Today is our first of the applications of the definite integral. We are discussing displacement and distance traveled. I'm going to begin with a reminder of some things from Calc 1. Okay, so Calc 1, let's recall. First of all, I have motion along a line here, and we will get to later in this video when you have motion in space. But for the moment, we're just motion along a line. P of t is position. And then if we take the derivative, P prime of t, this is v of t, this gives us velocity. Now, there's more to the story, which you might remember from Calc 1, which is you can take the second derivative of position, get acceleration, you can differentiate again, and the third derivative of position gives us jerk. But for the purposes of today, we really just need to focus on position and velocity. Okay, well, let's see what happens if I go the other way. So if we take a less than or equal to t less than or equal to b, and we integrate from a to b of the velocity dt. Well, I'm going to look at this more than one way. We can think about fundamental theorem of calculus, which is probably the way most people think about definite integrals. This would say find an antiderivative, evaluate at b, evaluate at a, take the difference. Well, here's an antiderivative, it's position. So we evaluate at b, evaluate at a, and take the difference. Okay, now this has a name, this here. This is the displacement on the interval. And what does displacement mean? So first of all, it's in our title of today, right? But what is it? What is this? Okay, first of all, displacement is a shift in position. And you see this here. It's just the final position, or the position at time b, minus the initial position, which is the position at time a, if you think about starting at a and ending at b. So just some shift in position, and because of this, it can be positive, negative, or zero. Even if your velocity is not necessarily zero the whole time, you can have zero displacement. For example, I could be right here, I could run like this, and then I could run like this, okay? And I wasn't running, but you get the idea that my final and initial position were the same, and so I would get zero for my displacement, okay? Now, what I want to do before we just jump into this one is I want to go back and see, without thinking about fundamental theorem of calculus, why when we integrate velocity, we get displacement, okay? Because this really uses the Riemann Sum, which all of the applications do, but it really uses the fact that the definite integral comes up in so many applications because of the Riemann Sum. This is why. So let's see it here, because it's something that it's good to remind ourselves of Riemann Sums. And we did some when we did Simpson's rule, trapezoid rule, but it's starting off this chapter. I want to make sure we're thinking about the Riemann Sum from the beginning. Okay, so let's say I have some velocity function here. We know the velocity can be both positive and negative, even with my little running back and forth example that I did. Here is my velocity function. Now, I mentioned, and I will do a Riemann Sum here. So what am I going to do? Maybe I will separate this. So let us subdivide. Let's subdivide. Maybe I'll just say subdivide. I'll stand over here. Subdivide the interval a to b A to B, into n subintervals of equal length my black is dying. I'll switch to blue. Of equal length, delta t, which is b minus a over n. And so this will give us, as you might remember from Riemann sums, it gives us some partition. So then we have, for example, a, which is t0 less than t1 less than, out to tn, which is b. And for example, we can choose n so large that the velocity, such that the velocity is approximately constant on each subinterval. Subinterval. Now, I will draw a picture here because it's always good to think about the picture. So I'm not going to pick n so large since the velocity is approximately constant for my picture because I wouldn't be able to draw something like that. I'm going to do one more. These are supposed to be equal length. And they're not quite. I either need to spread them out a little bit more or a little bit less. So here is my axis. There's A and B. Then I can put one here. Okay. That's going to be as good as it gets. Now, let's see. You can do a left, right. There's different Riemann sums you can do. I will maybe draw a right Riemann sum. Over here. Okay, so for example, here is a picture. Now, let me come up here. I will erase. Maybe I will erase everything except for what we're currently working on, which is the Riemann sum. Okay, so let's look over just a subinterval from ti minus 1 to ti. So on this subinterval, ti minus 1 to ti. Okay, well, what happens here? I'm trying to calculate displacement. If the velocity is, if we think about the velocity being constant, which I'm subdividing so much that is approximately that way, if you take the velocity, which is, say for example, feet per second, then you multiply by seconds, this gives you feet. Like if I ran, well, and I'll do an example momentarily, if you run the same velocity over time, you just multiply. So this v of ti times delta t, this is approximately the displacement on the subinterval. And again, as I mentioned, you could think about units. If this was in feet per second and this is in seconds, you see, in fact, you do have feet, okay? And it can be positive and negative. For instance, if I take one of these subintervals here, for example, my displacement is negative on that subinterval, and same with this one and this one, for example. Okay, so then we know how the Riemann sum works. We add, I goes from 1 to n of v of ti delta t. This will be approximately the total displacement on A to B. Or maybe I should say it differently. I will say displacement on A to B. The displacement on the whole interval is what I mean. Then we would take a limit as n goes to infinity or as delta x goes to 0. Those are the same statement. And we would get, we know the Riemann sum when you take a limit That's the definition of the definite integral. And so we get that, it follows that, the integral from a to b. Okay, well, now here's something that we're going to practice many times in this chapter, which is going from Riemann sum sort of notation and translating to an integral. What happens when you, this is the way I think about it, this sum becomes the integral sign. Okay, the delta t comes over here. In the limit, you write the dt. And then this, you just copy whatever function you see here, except without indices, like this. Okay, so maybe I will erase this. This is going from Riemann sum notation, and we think what's really happening is we're taking a limit. Okay, so we get that this is the displacement on a to b. And this, well, it should not be surprising. I had it up here already, but it's a different notion. That was fundamental theorem of calculus, and I wanted to connect it to the Riemann sum. Okay, so now let me talk about the other thing that was up here in the title, which is distance. And I will go back to this idea of running. So let's say, suppose I run forward 10 feet per second for 30 seconds. Then I turn around and run back at the same pace, and this is constant. Okay, and the question is, how far did I run? Now, I'm doing this on purpose with a constant so that we can really think about the question and not worry so much about what the integration or something like this. So this will help us just think about the question. Let's graph my velocity function. Let's see, I have a total of 30 seconds, well, 60 seconds, excuse me. I run for 30, so here's time, t, and then here's my velocity, and then coming back, we're down here, minus 10. Okay, so what happens is I start off from 0 to 30 here, and then right at the 30-second mark, well, there's this moment I turn around. In that moment my velocity would be 0. Then I start running, going back the other way. So this would be open like this. Something like this, okay? Well, this we can integrate quite easily because it's area, right? So the total displacement we know is 0. Without even integrating, because I started and ended at the same spot. Okay, I start, take off, and then I just turn around, take off this way. I start and end at the same place. So my displacement here, 0. And in fact, you can also see this here. The area, which we know the signed area is the definite integral, would be, maybe I'll write it, would be 30 times 10 plus 30 times minus 10, which is 0. I'll put that in parentheses because two different ways to think about it. Okay, but the distance is not 0 because I physically moved. So the distance in here, well, all that would happen on here, you see for the first 30 seconds, my distance is 300 feet. My distance traveled, we have 300 feet, 30, in fact, I'll write 30 times 10. And then on the second 30-second interval, which is here, I'm traveling 30 seconds, and I'm also traveling 10 feet per second. So it's another 30 times 10, which is going to be 300 plus 300. The total distance I traveled, I'm running out of space, is 600 feet. Okay? Now, this didn't really require calculus, but I wanted to do this so that we can see what the appropriate interval would be. So if you have, let's write it down, motion on a line, and you have the velocity function. So if you have motion along a line, and v of t is velocity, then we integrate, so well I should say for a less than or equal to t less than or equal to b, you integrate a to b of the absolute value, okay, absolute value of, oops, not a vector, just v of t dt. The absolute value, this gives the distance traveled, or equals the distance traveled. Let me switch back to blue, which is a stronger marker. I will apologize. Traveled. Okay? So this is this notion of displacement versus distance when you're in motion along a line. Displacement, you just integrate velocity function. Distance, you integrate the absolute value of velocity. So let us do an example, and then we will move into motion in space. Okay, so let's see what my example is over here. Okay, we want to find my example, we want to find the displacement and distance traveled by a particle with, let's see, we have velocity 6t squared minus 18t plus 12. 6t squared minus 18t plus 12. Oh, on interval is 0 to 2. So for t greater than or equal to 0, less than or equal to 2. Okay, well, the first thing we need is, or maybe I will start with displacement because it's a little more straightforward. We integrate 0 to 2 of the velocity function. Okay, so this is polynomial. The actual integral is not too bad. Sometimes the algebra of evaluating can be a place of mistakes, but the integrating is not too bad. So we have 2t cubed minus 9t squared plus 12t. And we evaluate between 0 and 2. Well, evaluating this function at 0, you see, is 0. And so when I evaluate at 2, I get 2 times 8, which is 16, minus 9 times 4. Well, maybe I'll write it. 9 times 4 is 36. So 16 minus 36 plus 24. So we have 40 minus 36, which is going to be 4. And I didn't really give units here. This would be, for example, maybe feet, or maybe meters, or maybe miles, because I didn't give any units. But we do have our displacement is 4. Well, now, for the distance traveled, I have to do a little bit more work. Maybe I will actually come up here and do some side work, because when you integrate absolute value, you have to figure out when is the function positive or negative or 0 and break it into a sum of intervals. Okay, so this is going to be my side work. Up here, my function is 6t squared minus 18t plus 12. I will set this equal to 0, or maybe I'll set it equal to 0 on this side so that I can factor here. I factor out a 6. And this factors into 6, t minus 2, and t minus 1. Okay? Now, then we have to think about, and this kind of thing we did in Calc 1 when we had to figure out like intervals of increasing, decreasing, and you take the derivative and see when it's positive, negative, 0, things like this. But in any case, so here I would have 6 and then I can, each one is going to be positive or negative, and then I will have v of t here. And then, well, okay, when we solve this, I didn't write that, maybe I should have. When we solve this, we get t is 1 and 2. Now, my interval is 0 to 2. And so I really just need to figure out here and here. So I could, for instance, evaluate this at 1/2 and 3/2. Okay, well, this is always positive. It's 6. This is 1/2 is negative, negative, and then at 1 we're negative, positive. So you see the velocity here is positive and negative. Okay, you could also just graph it, but I'm doing this with no graphing calculator. So what I see here is this is my function. It's positive here, and then it's negative here. Okay, so now I'm ready to go back to my problem. What I want is to integrate 0 to 2 absolute value of v of t dt, right? And this work, well, as I mentioned, it's like you did in Calc 1 to figure out increasing, decreasing, but I need to break this into a sum because when the velocity is positive, the absolute value of a positive number is itself, right? When the velocity is negative, then the absolute value of a negative number is actually negative, the negative or positive. So here, I see on 0 to 1, my velocity is positive. So I'm going to integrate velocity. Okay? But then on 1 to 2, my velocity is negative. So I'm going to have to integrate the negative, which in this case would be 12. Oops, it would be negative 12. Maybe I'll just put negatives in front of all of this. Minus 12 dt. I mean, another way you could do it, instead of how I did it, you could just put a minus and then put the velocity function. Now, be careful, because I have seen people who, they will think, oh, well, this is upper minus lower, upper minus lower. So when I evaluate out 1, everything's going to cancel out because I have a negative, I have a positive. Well, that's not going to happen because you would just get this, right? Well, it's not going to happen, I would say, generally. So take the time to evaluate this integral, evaluate this integral, and then add them up. Okay, so here, well, one thing that's nice, I already have an antiderivative, right? And in fact, I also already have my antiderivative evaluated at 2. That's this number 4. Okay, so this part I already sort of have. But in any case, this one, well, this is going to be, I have my antiderivative, or I could integrate again from 0 to 1. Okay, and then here, maybe now I will factor out the minus so I can just use the same antiderivative. Okay, well, when I evaluate this at 1, I get 2 minus 9 plus 12. Yep. And then here, minus, well, I've already evaluated it at 2. And then I subtract, well, here it is evaluated at 1. 2 minus 9 plus 12. Like this. And then I have to add all these numbers, and this is probably, or not probably, this is where my mistakes come, because it's really easy to mess up a minus sign somewhere. But 2 minus 9 plus 12, 14 minus 9 is 5. And we have another 5, and then we have a minus 4. So this is 10 minus 4, which is 6. Okay, good. So we have our, maybe I'll put this also in a green box. Here. 6 is the total distance traveled on 0 to 2. And then here with 4, this was the displacement on 0 to 2. And you notice that distance is greater than or equal to the displacement, and this is always the case, right? Next, let's move up in dimensions. So let's talk about motion in space. Okay. Now, this is also sort of a recall Calc 1. In fact, we spent time on this in Calc 1, but I will remind you of some things. So what changes is now position is a vector, say x of t, y of t, z of t, or you could just have two components. So as I have it written, we have motion in R3. Okay. We could just have two components, x of t, y of t, and it's motion in a plane, for example. Okay, and this is a vector. What that really means is that you have in x, y, z space, so this is x, y, and z axes, that you have, for each time, you have this x of t, y of t, z of t, maybe I will just write y and z. Okay, that's thinking about it as a point, but really what's happening is you have a vector, an arrow that starts at the origin and goes out to that point. So for every single time t, you have an arrow like this. Okay, but you can also think about it as points, really, vectors and points. There's a way to go back and forth, and it's in this picture. Well, one thing that we discussed in Calc 1 is the velocity, and this is a vector. Well, you just differentiate each component like this. And what else did we discuss from Calc 3? Well, you see, we discussed speed. And all of this looks like what we just discussed with the one-dimensional case. Because when I took that absolute value of velocity, really what that was that I integrated, it was the speed, right? Now this looks the same, except these bars, when there's a vector on the inside, is not absolute value. What this is this is the length, or another way to say this is magnitude. The magnitude of the vector, and this is the square root of x of t, x prime of t, x prime of t squared plus y prime of t squared plus z prime of t squared. This is the length or magnitude of a vector in R3. You can think about it here, the length of this vector, and this is literal Euclidean length. This distance from well, I should say distance, Euclidean distance, but the distance from the origin to this point x comma y comma z is the square root x squared plus y squared plus z squared, like this, okay? And this is how we calculate speed when we have motion in space. Okay, so I think we want to do an example now. Yes, let's just do an example to practice these notions. And this came off an old Calc 1 final. So a particle is moving in space with position P of t equals its square root t plus 1, then 2 cosine t, no, 2 sine t and 2 cosine t. 2 sine t, 2 cosine t, okay? And then we have a part A and a part B. Part A says find the velocity. Maybe we will do that here, and then I can put part B up above. Okay, part B. Compute the speed. Oh, this is at time t equals 0, so this would be initial velocity. And then part B, we want to find the speed, compute the speed. Okay. Very nice. This we will practice with these concepts before we get into displacement and distance traveled. Okay, well, the velocity at time t equals 0. First, we differentiate, and then we evaluate at 0. Okay, so the velocity as a function is, well, we differentiate each component. So this is 1 over the square, well, there's 2 square root t plus 1. And then the derivative of sine is cosine. The derivative of cosine is minus sine, like this. And here, technically, it was a chain rule, except the derivative of the inside function was 1. Okay, so I just wrote it kind of quickly. Okay, now we evaluate this at 0 to get the answer to part A, which is, this is a half, because 0 plus 1 is 1. And then the cosine of 0 is 1, and the sine of 0 is 0. Okay, so here is the answer to part A. Here, okay? Now part B. We want to compute the speed, and this is as a function of t. Well, we take the velocity and we compute its magnitude, and I will simplify this speed sum. Okay. Well, we take each component and you square them, and then you put them under a square root, add it up. So here we get 1 over, maybe I will show it in 2 steps, or maybe not. Maybe I will. T plus 1, 2 steps. I'll put a square root, then I will squared, and then we have, this one I will write as 4 cosine squared, and then when we square the negative, here, well, minus 2 times minus 2 is positive. Now, we can simplify. Let me erase this part. This sum, and this comes up fairly often or sometimes in these problems. You see, sine squared plus cosine squared is 1, right? So here I could, for example, factor out a 4, and then cosine squared plus sine squared would be 1. This term, this is just 1 over here. T plus 1 for example, then we'd have plus 4 because I didn't need this big square root. So cosine squared plus sine squared is 1. Okay, maybe I'll leave it like this. This is how I'll leave my answer. Simplified somewhat. So here is the velocity. The speed. You take the length of velocity, it gives us the speed. Okay, so this is this problem, and now let's get into the topics of the day. I think we're ready for that. Yes, which is displacement and distance traveled. Maybe I'll erase this also. Okay, so just like when we have motion in one dimension, we still want to figure out what is displacement, distance traveled, except we have motion in space. So we want, well, the displacement, and this is an important thing to think about here, and we want the distance traveled. Let me get the blue as it's a little darker. So for, let's say A less than or equal to T less than or equal to B, the displacement will still be P of B minus P of A. Okay, it will still be a shift in position from the position, the final position or the position at time B minus the position at time A. However, this is a vector because look, this is a vector, this is a vector. You take the difference, it's a vector. And I will say that when you subtract two vectors component-wise, just like when you integrate, well, we're going to get to that component-wise. Differentiate, we've already done component-wise, okay? So this is a vector, and this is an important thing to think about right now. Displacement, when you have motion in space, this is a vector. I'm trying to star it with every single color. It's a vector. Okay, maybe I didn't use red yet. Here I go. This is a vector. Okay, very nice. And then the distance traveled, this will be a non-negative number. Now, I mentioned when we were doing the one-dimensional motion that distance is greater than or equal to displacement. In this case, that doesn't make as much sense because this is a vector, this is a number, but it will be the case that the distance is greater than or equal to the, for example, length of displacement. We will make sure we see that in some exercises, for example. Okay, so this is a number, it's a scalar. Now, we want both of these. Maybe I should have written that at the top, but I will now. So we want both of these. We want these in terms of velocity. We want to find both of these, okay? Just like we had formulas, because sometimes you're not given a position, you're given just the velocity. And so we want to be able to find displacement and distance traveled just in terms of that. Now I have very good news for you. Is the formulas, they look exactly like in the 1D case. The formulas look like they do for 1D, like the 1D case. Except you have to understand we're in a different world. When I integrate velocity, I'm integrating a vector. When I integrate what looks like here, absolute value velocity is really a magnitude of the velocity vector. Okay, so displacement is the integral from A to B of the vector v of t dt, and the distance, total distance traveled, is the integral A to B magnitude of velocity dt, like this. Okay, this is what I was saying was the good news, because if, except for the hats, it doesn't look any different than in the one-dimensional case, except they're different, different objects, as I mentioned. Okay, so let's do an example. Oh, one more thing that let me mention that because it's going to come up in this example. Sometimes this is referred to as the length of the curve or the arc length. This is more common when you have a y equals f of x, and I will get to the problems like that where you're tracing out the length of a curve, but you can imagine if you follow a particle's motion. So we have a particle. Okay, imagine the end of this marker moving in space, and whatever it traces out over time, then this will be, think of it about being like a string. You stretch it out, and that length here, that's the distance traveled. Okay, that was a comment. Now let's do some examples. First example, we are given P of t equals cosine 4t, sine 4t, and 3t, sine of 4t, and 3t. And we want to find the distance traveled, or find the length of the curve for, let's see, for t between 0 and 2 pi. 0 less than or equal to t, less than or equal to 2 pi. Okay, great. So I will do this one. Then we will do one where we do both distance and displacement. Oh, and then we have a few more types of examples to discuss today. Okay, well, we know the distance traveled. This is going to be an integral 0 to 2 pi of the magnitude of the velocity vector dt. And so first, or the speed, if you think about it that way. The first thing I need to do is compute the velocity vector. I'll do that maybe down here. And then I'll be ready to integrate. Well, once I find its length, of course. First I find this, which we differentiate. When you differentiate cosine, well, it's a chain rule. We have minus 4 sine 4t. Then we have 4 cosine 4t and 3. Okay, then we calculate the length, and I do all of this simplification before I jump into the integral. That's me personally. Okay, so we have 16 sine squared t plus 16 cosine squared t. Oh, 4t. There's a 4t that I'm leaving off on, didn't mean to. Plus 16 cosine squared 4t plus 9. Now, this trick that I use, I don't know if it's a trick, it's just a trig identity that I used in the one that was up here that came from Calc 1, we can use here too. Because I have a sine squared plus a cosine squared, and so it's 16 sine squared plus 16 cosine squared will be 16. You could factor out the 16 if you wanted to see that. So this is the square root of 16 plus 9, which is 5. Okay, so this is an interesting function because it's moving at a constant speed, right? This is what we calculated. Now, it is not moving at a constant velocity because it's changing over time, but it's definitely moving at a constant speed. Okay, so this is an integral. 0 to 2 pi of just 5 dt, which would be 10 pi, like this. Okay, so this is our first example. Now let's do another one. Let's see, maybe I will erase this one. We'll do some more examples. Usually they're not that simple. We don't just integrate a constant, but it was a nice first example for distance traveled. Okay, so now we have the velocity is 3t squared t and 0, and this is between 0 and 3. And we want to find part A, the displacement, and part B, the distance traveled. So we will get to practice here both parts. Okay, this is good because in particular we have to think about, we haven't yet integrated a vector. Well, all you really do is you just integrate each component. So the way I will write it, it's not the only option. I have an integral, 0 to 3, of the velocity, dt. It's a vector. Well, you can, maybe I'll just do the integral because this is pretty not hard to integrate each term. You just integrate each term. This is t cubed. This is t squared over 2. And this is 0. Then you evaluate between 0 and 3. Now, this is vector subtraction, which is component-wise. So I evaluate at the upper limit, 27. Evaluate at the lower limit, 9/2. Then we have 0. Then we subtract. Well, in this case, we get 0 at the lower limit of integration, but I still wanted to show it, to show the steps. And then how we would subtract these two vectors, we would just say 27 minus 0, 9/2 minus 0, 0 minus 0, like this. And we have our answer. So the answer here is just 27, 9 over 2, and 0. Okay, now for part B. Part B. We need to integrate the length or the magnitude of velocity dt. Okay? So we have velocity. We don't need to differentiate here. We start with velocity. So we can just start by finding the length, which is the square root of, well, it's 9t to the 4th plus t squared. Okay, so now the question is, how am I going to integrate this? And this is usually maybe what makes these problems a little more tricky is you really have to think about integrating what's underneath an absolute value, which, as we know, is not always easy. But we want to simplify, simplify, simplify so that we can integrate. Here, for example, both terms, I can factor out a t squared, and then I have a 9t squared plus 1. And now, look how nice this is going to be. Maybe I should actually do this below so that I have room for my integral. T squared, 9t squared plus 1. And then you can factor the t squared out here, and it becomes a t. And then we have a square root, 9t squared plus 1, like this. Now I can integrate the integral. Well, we don't integrate. We integrate this function, that's what I meant to say, of t. dt. Okay, well, this is something I am prepared to integrate. This is substitution. So maybe, I don't know where to put my box. Maybe I will do it in red. We'll do it right here. I have some space. Okay, so my u, 9t squared, I might need a little more space, plus 1. And then du is 18t dt. Now what do we have in our integral? We have t dt, which is going to be a 1 over 18 du is t dt. Now I always change my bounds with substitution. When t equals 0, u equals, 1. And then the final one is when t equals 3, u equals, well, let's see, 9 times 9, 81 plus 1, 82. Okay, so here is all of my work for the substitution. Now, because I'm going to change my bounds, I never have to go back to t. Okay? And now we come back to this integral here. This is an integral between 1 and 82 of u to the 1/2 times 1 over 18 du. Maybe I will box this off too. I've got side work for this problem in so many different places. That's okay. Trying to keep everything clear what I'm doing at each part in the board. Now I integrate. So this is, we have a 1 over 18. We add a power. Divide by the higher power. Evaluate between 1 and 82. And this becomes, let's see, 1 over 27. So 1 over 27. Then we have 82 to the 3/2 minus 1 to the 3/2, which is 1. This is an exact answer. So this is the exact answer of the total distance traveled. Okay. Now, it's going to be the exact same concept, except it's going to look different. So now suppose, and this is what I mentioned, I briefly mentioned this when I mentioned arc length. So suppose I have a function y equals f of x, and I'm interested, this is what we typically use the terms arc length. And this is literally distance traveled from, let's say, x equals a to x equals b. Now, what does this mean? You have some a, some b, some function. Okay, what it means is that you start at the point a, so this is a y is f of x. You start at a, comma, f of a, and you end at b, comma, f of b. And the whole time you are walking along the curve. Maybe I will keep with my green. So we walk along the curve like this. Okay, walk along the curve and ask yourself, what's the distance you traveled, or how far did you walk? This is the arc length, okay? So this is the exact same notion. So this is arc length here. It would be the length of this, if you stretch that out, the length of that string, just as I was discussing not that long ago. Now, as we look at it, we do not see it parameterized, for example. We don't see a t. So we will have a formula for arc length, which involves an integral. And it will come from just y is f of x. But to see the formula, we can really think about the vector version. Because look, this green curve between a comma f of a and b comma f of b is motion in space, right? So to get the formula you can consider a particle with P of t equals, well, let's look at the coordinates. If t goes from, well, I will, so a less than or equal to t, less than or equal to b, this first coordinate is just my t, and then the second coordinate would be f of t. And you see, looking at this, this is exactly all ordered pairs. This is what's lying on the graph, right, between a and b. This is, we are tracing out the curve with this particle, okay? So then the arc length, now I have something parametric to think about. The arc length here is just the total distance traveled by this particle. So let's get a formula for it. We find the velocity. Here it's 1 comma f prime of t. And then we integrate absolute value, or excuse me, length of the velocity dt, which is an integral a to b, let me move back to blue, of the square root, well, I take the components, square them, and add. So this is 1 plus the derivative squared dt. Okay, so we have just derived, if you want to think it that way, we have shown, thinking about this parametrically, what arc length is. Okay, so let's write it, the arc length. Except I'm going to write it in terms of x, because y is a function of x, is the integral a to b square root 1 plus the derivative squared dx, like this. And just like when you are doing the vector valued, if you start with a particle, either position or velocity, and then you calculate its magnitude and work like that, or if you start with a y equals f of x, the hardest part of these problems is simplifying what's underneath the square root so that you are able to integrate it. So let's do some examples of this type. Oh, okay, I have one example I have prepared, and then I will say that I have, this is one of the topics I have an example video on. I will put at the very end of this YouTube video, it will pop up and you can click and you can watch a few more examples. But let's do one of this y equals f of x form. And this example comes from trigonometry. Okay, so example, we have f of x is ln of secant of x, and we want to find the arc length on 0 to pi over 4. Now, I will have to just tell you an integral when we get to that point. We didn't spend all that much time on trig integrals, but it's one that maybe I'll take the time to justify. Oh, yeah, okay, we will, fine. But let's get the problem set up first. Okay, well, you see, the first thing, well, I can set it up, right? I know it's going to be an integral 0 to pi over 4 square root 1 plus f prime of x squared dx. But just like if I was working with a vector valued function, I'm not just going to jump into the integral. First, I'm going to work with 1 plus the derivative squared and simplify it. Then I will take a square root, then I will go into the integral. Okay, so this is a chain rule. Right, the inside function is the secant. When we take the derivative, we get 1 over the secant, and then the derivative of secant, I hope you remember secant tangent. So this is secant x tangent x. Okay? Well, the secants cancel and we get 1 plus the tangent squared of x. I want to simplify this before I take a square root so that I'm able to integrate. Now, there is a, this is problem one. I like this problem because we have to really think a lot about trigonometry here. But what do we know for trigonometry? And in fact, we have even used today. We know that sine squared plus cosine squared equals 1. And this is true. This is an identity, right? Well, I can divide by different things to get 2 more identities from trig, and one of them is here. So if I divide the whole thing by cosine squared, maybe I'll write that. Let's divide this by cosine squared of x. Okay, what do I get? Well, the first term, sine squared over cosine squared. This is the tangent squared. Cosine squared over cosine squared is 1. 1 over cosine squared is secant squared. Okay. So now I have a way to simplify this. 1 plus tangent squared is the secant squared. Now you see it's going to be very nice to go to my integral, because if I integrate 0 to pi over 4, the square root of the secant squared, well, on 0 to pi over 4, the secant is positive. So the square root of secant squared is just the secant. This is an integral, 0 to pi over 4 of secant x dx. So maybe I will, I was going to tell you, but I have space. So let's come down here and do the integral of the secant. It takes a trick. This is one, let's say you have the secant appear on an exam. I would give you the antiderivative for the secant, okay, or a quiz. It's not one I expect you to memorize, but it's one that once you see the trick, you could remember and do yourself. Okay, so I want this. Now, I am going to do this with a trick. As I mentioned, I am going to multiply by 1 of the form secant x plus tangent x over secant x plus tangent x. Right, when I multiply by 1, I have not changed anything. This is still this. But now I multiply through, this is the integral of secant squared plus secant tangent. And in the denominator, I have secant tangent. Secant plus tangent. Now, this I can integrate, and I will run out of space, but maybe I can put it up here. This, you see, look, u is the denominator. Oops. Then du, well, the derivative of secant is secant tangent. The derivative of tangent is secant squared. And don't forget, there's a dx. Okay, so look. This is secant tangent plus secant squared dx. So this is exactly, we have a 1 over u du. Okay, do you see it, right? This integral, maybe now that I have to extend my box anyways, I will give myself some space. This is literally the integral, 1 over u du. Okay, well now we know how to integrate this. It's ln, absolute value of u plus c. And now we just go back to x. So this is ln, absolute value, secant x plus tangent x plus c. Okay, so what have we found here? I have to extend my box significantly more than I thought I would, but that's okay. We have just derived, and I mentioned it took a trick, but once you see it, it's one that maybe you can remember, but I mentioned you can also, I would just give you the secant if you ever needed it. We have an antiderivative for the secant, which was what I was trying to do. Okay, now let's return to our problem, okay? So like I said, you could have just looked it up. The problem though, let's go. Well, this would be ln absolute value secant x plus tangent x evaluated between 0 and pi over 4. And now we need to think about these two things. Maybe at this point, I will erase this box just so I have the space to finish my problem. Okay, so then we have ln the secant of pi over 4, oops, plus the tangent pi over 4. Well, I could have taken off my absolute values. Secant and tangent are both positive at pi over 4, but in any case, it's fine like this, minus ln the secant of 0 plus tangent of 0. Now, maybe it's good I erased the antiderivative so I can draw my unit circle and we can remember what happens at pi over 4. Well, in fact, I really only need to draw the first quadrant. Pi over 4, the sine and the cosine are the same, and they are square root 2 over 2, comma, square root 2 over 2. This is for the angle pi over 4. Okay, which means secant, which is 1 over cosine, is 2 over square root of 2, which you could simplify if you wanted, although it's fine like that. And the tangent is 1. Sine and cosine are equal. And then here, the secant of 0, this is 1. The tangent of 0 is 0. Natural log of 1, excuse me, is 0. And so we're left with just this, ln, maybe I'll drop my absolute, I'll leave them. Doesn't matter, the number is positive, like this. And you could simplify, as I started to say, 2 over square root of 2 is just the square root of 2. But in any case, this is a fine answer here. So this is the arc length for this problem. Now, I would say, let's see, where will I put it? Go here. And you can see a few more examples of distance traveled and arc length.